In today's class, we will continue our discussion on motion in a straight line. We will look at some examples from the topic we had covered in the last class. Then we will look at the concept of relative velocity and some more examples. So, in the last class what we had seen was that if a particle is moving along a straight line and it has a uniform acceleration a, and if it starts with the speed of v0, then the velocity which we have at the end can be at time t can be given by expression v is equal to v0 plus at, where v is the velocity at time t. The distance covered during this interval, which we write by x minus x0, this can be given by v0 t plus half at square. And if we know the two velocities, the initial velocity and the final velocity, and if we know the acceleration and the distance, then the relation between these goes by v square is equal to v0 square plus 2a times x minus x0. A couple of more relations can be worked out, and this is if we know the initial velocity and the final velocity and the time taken, then the average velocity, because the acceleration is uniform, can be given as half of v0 plus v, and therefore the distance travelled will be half times v0 plus v times t. And similarly, if we know the distance and we know the final velocity, we do not know the initial velocity, then the relation takes the form x minus x0 is equal to vt minus half at square. Now, in all these formulas we are assuming the acceleration is a. Now, you should realize the body could be undergoing a negative acceleration, which we call as retardation, and then you have to replace the a with minus r, where r is the retardation. So, that sign also has to be accounted for, and if somewhere you have a minus sign and it is retarding, then the net of this will become a plus sign. So, these sort of things you have to take care. Another thing we have to be careful about is that these formulas are valid only if the acceleration is constant. If the acceleration is not constant, we cannot use these formulas. And also what you observe in each of these formulas, for example, if we look at this formula, in this formula distance is missing. We have the two velocities, acceleration and time. So, if we look at our case, we have the final velocity, initial velocity, acceleration, time, and the displacement or the distance, this is x minus x0. These are our 5 variables, and in each of these formulas you will find that 4 of these variables come, 1 variable is not there. So, therefore, depending on what is given and what is asked for, you have to use an appropriate formula. Normally, the first 3 formulas are enough. The other 2 formulas directly fall from the first 3 formulas, and we use these. And sometimes for the displacement, instead of x minus x0, you will find s symbol being used, and so people remember these formulas. S is equal to v0 t plus half a t square. Let us take an example now. The problem says a ball is dropped from the roof of a building with 0 initial velocity. An observer stands in front of a 100 centimeter high window, and he observes that the ball takes 0.2 seconds to fall from top to bottom of the window, and then it touches the ground 1 second later, and we have to find the height of the building. And it is given that we can assume the value of acceleration due to gravity is equal to 10 meters per second square. As we discussed in the last class, these are the problems where a body is falling freely under the influence of gravity. That means in the vertical direction, the acceleration which it is observing is equal to g towards the ground. Let us now solve this problem. So, what we have is that this is the building from where the ball is falling. Let us choose the x direction downwards. So, therefore, the acceleration is equal to plus g, which will be 10 meters per second square. Now, what is given to us is that the ball starts to fall, let this position where the ball starts to fall, let that be 0. Let the position at top of the window be 1, let the position at bottom of the window be 2, and let the ground position be indicated by 3. So, now what is given to us is that during this distance from 1 to 2, this distance is given to us as 100 centimeters, which is equal to 1 meter. And we also know that the time period during this time is 0.2 seconds. So, now what we realize is we know the distance, we know the time, and we know the acceleration, but we do not know either the initial velocity or the final velocity. So, therefore, we use the formula that x minus x 0 is equal to v 0 t plus half a t square. This is the formula. So, now we use this formula from on the distance from 1 to 2. So, therefore, now from 1 to 2, x minus x 0 will be 1 meter. The initial velocity v 0, which we do not know, this will be v 1. The time taken from 1 to 2 is 0.2, and then we have plus half times acceleration is g, and the time taken from 1 to 2 is 0.2 square. Now, this g we know this is 10. So, therefore, the only unknown in this equation is v 1, and when we put in the value, what we get is 1 is equal to 0.2 v 1 plus 5 times 0.2 square, and from here we will get the value of v 1 as 4 meters per second. So, once we know the value of v 1, then we have to find the total height of the building. So, what we can do is let us divide this, let us say this is S 0 and let this remaining height be S 1. So, S 1 includes the height of the window and from bottom to the ground. So, now what we can do is we know the total time from 1 to 3, this is equal to 1 plus 0.2 is equal to 1.2 seconds. So, we use the same formula again, that x we use the total distance, which is now S 1 is equal to, now we know the velocity 4 into 1.2 plus half into g into 1.2 square. So, using this, when we work this out, we will get S 1 is equal to 4.8 plus 7.2. So, this becomes equal to 12 meters. So, this is the height from the top of the window to the ground. Now, to this we have to add S 0. So, therefore, we now move on to calculate S 0. This is the height or the distance from, I should rather replace height by x, from top of the building to top of the window. Now, it turns out what we know here in this case, if we go back to our schematic sketch, what we know is that the ball is starting from rest. So, we know the velocity at 0, we know the velocity at 1. We know these two velocities, but we do not know the time which we knew in the other cases which we have done. So, therefore, we use the formula that we know. So, we know v, we know v 0 and we know the acceleration, and so we can use this to find the distance x minus x 0. So, we use the formula v square is equal to v 0 square plus 2a times x minus x 0 is s 0. Now, V square was given as 4, V was given as 4. So, V square is 16, this will be equal to 0 plus 2 times 10 times S0. So, from here what we get is S0 is equal to 16 divided by 20, this was equal to 0.8 meters. So, therefore, we get the total height is equal to 12 plus 0.8 is equal to 12.8 meters. So, now, well, we have obtained this solution using one set of formulas. Someone else could have divided this distance from 2 to 3, worked out, because we know the time and the velocity at 1 and the distance. So, we could have used this to find V2, and from V2 could have gone to ground, found this remaining distance, added that to the height of the window, and to that added S0. And so, there could be more than one ways in which the same problem can be solved. What you have to look at is how do you optimize the variables and try to solve the problem in minimum number of steps. Let us now look at another problem. And here what is given to us is that a train travels from station A to station B. It starts from rest at A, undergoes constant acceleration A1 in its first part of motion, and then it undergoes constant retardation A2 till it comes to rest at B. It says find the total time of the journey in terms of A1, A2 and L, the distance between A and B. And it is to be assumed that everything is in a straight line. So, when we look at this problem, well, one of the common mistakes which students tend to make when they do this problem is it says the first part of the motion, and somewhere they assume that this is the first half of motion. It is half the distance. Nowhere in the problem it is given that the distance which it travels from A to B, that half of it is acceleration and half of it is retardation. The particular part where it is acceleration and the particular part where it is retardation is not given to us. So, therefore, we have to keep that in mind when we work this problem. So, let us solve this problem. So, let us see the solution. So, here what we do is, let us say the train starts from A, it moves to B. If we look at its velocity, so it moves from A to B, let us say the point where it, let the point be C, where it changes from acceleration to retardation. So, if we look at draw the velocity time curve, here if we plot velocity as a function of time, then what we will find is when the train goes from A to C, the velocity increases, and it is increasing because it is uniform acceleration, this will be a straight line, and once it approaches C, at C, then the velocity reduces. So, this is with an acceleration A1, this is with acceleration of minus A2. So, because there is a retardation of A2, which means acceleration is minus A2, and the distance C is somewhere between A and B, the point we do not know where exactly it lies. So, what we know is that this total distance is L. So, now if AC we can write as S1 and CB as S2, what we know is S1 plus S2 is equal to L. What we also know is velocity at point A is 0 and velocity at point B is 0. So, therefore, let us say the velocity at C be Vc. Then if we work out, what we know is Vc square will be equal to Va square plus 2A1 times S1. And we also know Vb square will be equal to Vc square minus 2A2 times S2. So, from here what we can get is S1 is equal to, now also what we know is VA is 0 and we know VB is 0. So, the first equation will give us S1 is equal to VC square upon 2A1, and the second equation gives us S2 is equal to VC square upon 2A2. So, what we know is this total distance is L. So, therefore, L is equal to VC square upon 2A1 plus VC square upon 2A2. S1 plus S2 is L. So, what we are doing here is we know L, we know A1 and A2, we have to get our answers. So, from here what we get is VC square into 1 upon 2A1 plus 1 upon 2A2 is equal to L. So, we have got VC, L in terms of VC. So, this gives us VC square is equal to L times 2A1 A2 divided by A1 plus A2. So, when you simplify you will get this. Now, we have to find that the question is not to find VC. If the question was to find VC, we had got the answer. Now, we have to find the total time. This was the problem. So, to find the time, once I know VC, what I know is VC is equal to VA plus A1 T1, where T1 is the time taken from A to C. T1 is time from A to C. And we also know from this VC that VB is equal to VC minus A to T2. So, from here once again we know VA is 0, VB is 0. So, what we have is T1, from here what we get is T1 is equal to VC upon A1 and T2 is equal to VC upon A2. Notice because we had retardation, so we have already used minus A2 here. So, now we have to find the total time. So, total time is equal to T1 plus T2. So, this will be equal to VC times 1 upon A1 plus 1 upon A2, and we have already, we know VC square, VC is equal to square root of L times 2 A1 A2 divided by A1 plus A2. So, we can substitute in here and simplify, and we will get our final answer. Once we simplify, we will get T is equal to square root of 2L A1 plus A2 divided by A1 A2. Now, in problems like this, you have to see what is given and what is asked for and work out accordingly. Now, the same problem we can have a second method for solving this problem, and that will be we can solve it using the graphical method. Let us now solve this problem using a graphical approach. In a graphical approach, what we do is, given the variables which are given to us, we try to plot them and then see if we can find the quantities of interest. So, in this problem it is given to us that the train travels and its acceleration is given during the duration of its journey. So, if I look at the acceleration and plot it as a function of time, then what is given to us is the train travels for the first part of its journey with an acceleration a1, and for the second part of its journey with an acceleration of minus a2, because it is given to us that the retardation is a2. So, acceleration versus time curve looks like this. Now, the way we exploit the graphical method is that we use the fact that area under the acceleration curve gives us the change in velocity, and the area under the velocity and time curve gives us the displacement. And similarly, the slope of the velocity and time curve will give us the acceleration at that point. Now, when acceleration is constant, then velocity and time curve will give us a straight line with a slope which is equal to acceleration. So, in this problem, when we plot the velocity and time curve, the train starts at station A, it stops at B. Let C be the point where it changes its acceleration. So, it starts with a 0 velocity, and because the acceleration is constant from A to C, it will travel, the velocity and time curve will look like a straight line with a positive slope. And when it moves from C to B, this will be another straight line with a negative slope, or so here in this curve the slope will be A1, and in the second part of the curve the slope is equal to minus A2. And now let us look at the problem. In the problem, what is given to us is we have to find this total time from A to B. That means if we say this time is T1, if this time is T2, we have to find the sum of these times, that is T1 plus T2. And what is given to us is the total distance which is travelled is given as L. Now, distance is also the area under the velocity time curve. So, therefore, if I look at this area, so now let us say the velocity at this top point is Vc. So, let us use this information. If this is Vc and we drop a perpendicular from here, so area under the Vt curve, this will be equal to half multiplied by Vc multiplied by t, where t is equal to T1 plus T2, the total time. And this is given to us, this is equal to L. So, this L is given, T is what we have to find, and Vc as of now is not known. So, here we get one relation, we want to find the second relation. The slope of the line here is A1. Now, the slope of the line will be given by the velocity at point C Vc minus 0 divided by T1, and this is equal to A1. This is slope of the first line, and slope of the second line, which is basically Cb, this will be given as 0, the velocity at B, minus Vc divided by T2, and this is equal to minus of A2. So, from here what we get is, when we write this, what we get is T1 is equal to Vc upon A1, and we get T2 is equal to Vc upon A2. So, from here what we get is T1 plus T2 is equal to Vc upon A1 plus Vc upon A2, which we can write it as Vc into 1 over A1 plus 1 over A2. And now, we use the second relation which we have, that half Vc is also equal to L divided by 2t. This we had got earlier. So, therefore, what we get from here is t is equal to, so we substitute the value of Vc in here. So, we will get t is equal to L upon 2t times 1 over A1 plus 1 over A2, and now we can take t on the other side. This implies t square is equal to L upon 2 into 1 over A1 plus 1 over A2, and this is the answer which we had got earlier also. So, therefore, the graphical method can be useful if we realize two things, that slope of the velocity time curve gives us the acceleration, and the area under the velocity time curve gives us the displacement. Now, let us focus our attention on the concept of relative velocity. And what we realize here is that position of a point depends on the reference frame from where it is being measured. So, therefore, position is a frame dependent quantity, because it will change with the reference frame with which you are measuring. And because position is a frame dependent quantity, this also implies that velocity and acceleration of a point, which are derivatives of the position and the velocity vectors respectively, they also become frame dependent quantities. And this we have observed when we sit in a train. When we sit in a train, we are in the reference frame of the train, and it is a common experience that we see that the trees which are there and the telephone pole, they appear to be moving when we are sitting in a train. Whereas to a person who is on the ground, clearly the train is moving and the telephone poles and the trees are fixed. So, therefore, the movement of a point becomes a function of the frame from where you are observing that point. That means the velocity which we measure will depend on the reference frame. It cannot be, we cannot talk of any absolute velocity in that sense. So, let us consider a point P moving in a straight line. For the purpose of this unit, we are talking of motion in a straight line. We will talk of motion along a curve, etc., with regards to moving frames when we talk of those topics. So, here we are considering motion of a point P along a straight line. So, now we have an observer attached to frame A, and along with the observer, so that means we have a reference frame A, and from where there is a point P, this observer is considering the movement of point P. So, the location of P as measured by frame A, we denote that by XPA. So, XPA is the location of P as observed by observer attached to frame A. Now, let there be, so this is frame A, we also have a frame B, and the position vector of P as observed by frame B, let us write that by as XPB. So, XPB is the location of P as observed by observer attached to frame B. And the position of frame B with respect to frame A, we denote it by XBA. So, XBA is the location of B as observed by observer attached to frame A. Notice in all this, the first point, there are two subscripts. The first one represents the point which is moving or the point which is being observed by both the frames. The second one represents the frame from where the measurements are being taken. So, now here from the figure it is very clear that x PA is equal to x PB plus x BA. So, we have here, let us write this, x PA is equal to x PB plus x BA. Now, if we differentiate with time, then what we get is dx PA by dt is equal to dx PB by dt plus dx BA by dt. And this we can write as VPA is equal to VPB plus VBA, where VPA is the velocity of P as observed from frame A, and VPB is the velocity of P as observed from frame B, and VBA is the velocity of the frame B as observed from frame A. Now, often what will happen is frame A in a lot of cases will be fixed to ground, and if this is obvious that it is the same frame, then A may be dropped, because when it is clear that frame A is fixed and is an obvious frame, then we do not write this, and then the relation will become Vp is equal to Vp with respect to B plus V of B. So, which means velocity of point P as observed from ground is equal to velocity of P as observed from frame B plus velocity of B as observed from ground. So, this, and in this what we realize is this gives us a relation that velocity of point P as observed from frame B is equal to velocity of P minus velocity of B. So, this is this. So, this we can write velocity of P as observed by frame B is equal to velocity of P minus velocity of B, where if nothing is said, that means they are being measured with respect to ground. Now, if we assume if both frames A and B move with constant velocities, that means acceleration of A and acceleration of B are both 0, then this leads to the relation that if both of these are 0, what we will get is acceleration of P with respect to A is equal to acceleration of P with respect to B plus acceleration of B with respect to A. This we get by differentiating the velocity expression, and because acceleration of B with respect to A will be equal to, this term will be AB minus AA, and since both of them are 0, what we get is acceleration of P with respect to A is equal to acceleration of P with respect to B. That means if the two frames are moving with constant velocity and you look at the acceleration of a point P which is moving with respect to these frames, if the frames are moving with constant velocities, then you will measure the same acceleration by both these frames. Now, this discussion on relative velocities, here we have done only for 1D motion, but we will do similar discussion for 2-dimensional motion. And the reason why acceleration and this the measurement of motion with respect to frame becomes important is that eventually we will use these relations of acceleration, we will relate this to force, and we have, for those of you who know, Newton's second law, which says force is equal to mass times acceleration. And there we have to be very careful, because when we say force is equal to mass times acceleration, then acceleration cannot be measured with respect to an arbitrary frame of reference. Acceleration has to be measured with respect to a frame which is fixed. We call that as inertial frame, and we will discuss that when we come to acceleration. Another word of caution, when we use this relation VPA is equal to VPB plus VBA. This relation is valid for low speeds, and by low what we mean is when VPB and VBA, each of them are much less than c, where c is the speed of light. If these velocities, if the magnitudes approach the speed of light, then this relation does not work, and we have to use the theory of relativity to work this out, because when we approach speed of light, what theory of relativity tells us is that nothing can have a speed which exceeds the speed of light. So, we have to be careful. Next, let us look at a couple of examples in relative motion. So, the first example which we have is a person walks up a stalled escalator. So, there is an escalator, and if a person walks from bottom to the top, he takes time t1. Now, it is also given that on a moving escalator, if the escalator is moving and if the person just stands there, then he reaches from bottom to top in time t2. Now, we have to find the time if the person is moving at the speed which we have specified and the escalator is also moving, then how much time will the person take to go to the top. So, this is what we want to find out. So, we have here person moves up on a stopped escalator in time t1, and the escalator itself to go from top to bottom, bottom to top takes a time t2. And now we put, if the person moves with his speed on the moving escalator, find the time t3, and it is given to us that the length of the escalator is L. So, let us work this out. Let us first find velocity of the person when the escalator is stopped. So, this we know that velocity of the person is equal to the total length of the escalator which he travels divided by the time t1. Now, when the person moves on the escalator, then this Vp becomes velocity of the person with respect to the escalator. And so, on a moving escalator, with person moving, velocity of this person with respect to the escalator is equal to L upon T1. And the velocity of the escalator by itself, this is given as L upon T2, because just the escalator by itself takes a time T2. So, now when the person moves with the escalator, velocity of the person with respect to ground, this will become equal to velocity of the person with respect to escalator plus velocity of escalator with respect to ground. So, this will become equal to L upon T1, and this is given as L upon T2. And velocity of the person with respect to ground now will be given as L upon T3, where T3 is the final time taken by the person on the moving escalator. So, from here what we get is 1 upon T3 is equal to 1 upon T1 plus 1 upon T2, and we can get T3 is equal to T1 T2 upon T1 plus T2, and we realize the final answer here is independent of L. So, we can find the time taken by the person on the moving escalator. Now, let us look at another problem. Two towns A and B are connected by a bus service, with bus leaving in either direction in T minutes. A person is cycling at 20 kilometers per hour in the direction from A to B, and he observes a bus going past him every 18 minutes in his direction of motion and every 6 minutes in the opposite direction. Now, it is given that the bus speed Vb is constant. We have to find Vb and T. So, the bus speed is given which is constant. We have to find the bus speed, we have to find the time period between buses. The speed of the cyclist is given to us. So, let Vc be the speed of the cyclist. This is known to us. We also know the time T1 when buses pass after this time in the direction of the cyclist, and time T2 is the time when buses pass the cyclist in the reverse direction. So, T1 and T2 are the distance between passing of successive buses. So, and let Vb be the speed of the bus. So, let us solve this problem. We use method 1, where we will analyze everything in a fixed frame of reference. So, let us see, when the cyclist, let us say, is at some position and one bus passes him. So, bus number 1 passes him and the cyclist is at t is equal to 0. Now, the next bus, which is bus number 2, is at a distance of Vb times capital T at this instant behind bus number 1, because all buses are crossing after time t. Now, what is told to us is, when the cyclist, he sees the next bus after time t1. So, the distance travelled by the cyclist during this time t1 will be equal to Vc into t1, and the distance travelled by bus number 2 during this same time, this will be equal to Vb times t plus Vc times t1. And this total distance which is travelled by bus number 2 is also equal to, so therefore, let us write this, the distance travelled by bus 2 when it crosses the cyclist from t is equal to 0 time observed at that time, this will be equal to Vb times t plus Vc times t1. And during this time, how much is the time this bus has travelled? This bus has travelled for time t1. So, this is equal to Vb times t1. So, therefore, we get one relation from here. This is relation 1, and we now analyze the other side. Now, if we look at this relation, there are two unknowns Vb and T. Vc is given to us, T1 is given to us. So, in this relation we have one equation, but two unknowns. So, we need one more equation, and for that we look at the buses travelling in reverse direction. So, now here let us say at t is equal to 0, a bus number 3 has just crossed the cyclist, and there is a bus number 4. This will be at a distance of Vb times t behind bus number 3. In the cyclist is moving like this. Now, what happens is, after a time t2, the bus number 4 will cross the cyclist. Now, the distance, this distance which the cyclist travels is equal to Vc times t2, and the distance travelled by the bus here, this is Vb times t2, and the total distance is Vb times t. So, what we get is the second relation, which gives us Vb times t is equal to Vc times t2 plus Vb times t2. So, now once again if we count, we have the same unknowns Vb and t2 unknowns. Vc is known to us, t2 is known to us, Vb is the same unknown. So, therefore, when we work this out, we have two equations and two unknowns, and we can solve this and we will get our answer. So, this is one way of solving it, and you can now eliminate the. So, for to solve this, for example, in this case what we have, if we have to solve this, equation number 1 gives us Vbt is equal to Vb minus Vc times T1, and equation number 2 gives us Vbt is equal to Vb plus Vc times T2. We equate these two, that means the left hand side will go away. So, from here 1 is equal to 2 will give us the value of Vb, because we know Vc, T1 and T2, and then we can find T. Now, the same question, we can work out the numbers. When you work out the numbers, please remember you should have consistency in units. If you are expressing time in hours, for example, in the data specified in this question, we have the velocity is given in 20 kilometers per hour, whereas the time is given in minutes. So, therefore, it is best to convert everything. If you are talking in terms of hours, we should convert the minutes to hours. Now, let us look at a second method of solving this problem. The second method is, let us observe the motion of the bus in the frame of the cyclist. So, let us look at the first motion when the bus and cyclist travel in the same direction. Then, so this is the bus travelling, this is Vb, and the cyclist is travelling in the same direction, which is given by Bc. So, the velocity of the bus as seen by the cyclist, this we will put as Vb with respect to c, this will be equal to Vb minus Vc. And in this frame, when we look at it, when the cyclist is travelling, to him it will appear, to the cyclist, the bus travels Vbt, the distance between two successive buses, when it overtakes him. So, the distance in the frame of the cyclist which is there is Vb times t. And if you have some difficulty in trying to understand this, you assume that the cyclist is at rest. If the cyclist is at rest, Vc is equal to 0, and then he will see one bus, let us say bus number 1 when it crosses him, after that when bus number 2 crosses, this bus number 2 is at a distance of VBT away. So, the distance travelled by this bus before it crosses him will be VBT, and the same thing will continue when the cyclist is moving. And so, now in this reference frame the distance travelled is VBT and the time taken is T1. So, therefore, we have the velocity of the bus as seen in the cyclist frame multiplied by the time. This will be equal to the distance travelled by the bus as seen in frame of the cyclist, and this will be equal to Vb times T. So, we get Vb minus Vc times T1 is equal to Vbt, and this relation is the same which we have observed as equation number 1 earlier. Now, let us look at the motion in the reverse direction. So, the cyclist is moving like this, the bus is moving in the opposite direction. So, here now the velocity of the bus in the ground frame, this is equal to minus of Vb. The minus sign comes because we are assuming this as the positive x direction. Now, the velocity of the bus as seen by the cyclist will be equal to velocity of the bus as seen from the ground minus velocity of the cyclist as seen from the ground. So, this will be equal to minus Vb, and velocity of cyclist as seen from ground is Vc in the plus direction. So, with the minus sign it becomes minus of Vb times minus Vc, and this becomes equal to minus of Vb plus Vc. So, this is velocity of the bus as seen by the cyclist. Now, in the reference frame of the cyclist, the bus travels minus Vbt before it crosses him, and this is when the first bus number 3 crosses him, that is when we start t is equal to 0, and this is bus number 4. So, as the cyclist observes, the distance travelled by bus number 4 before it reaches him will be minus Vbt. The minus sign comes because the bus is travelling in the opposite direction. So, now that we again use the fact that velocity of the bus with respect to the cyclist, this time taken is T2, and this will be equal to minus Vbt, and velocity of bus as seen from the cyclist we have already worked this out. This is minus of Vb plus Vc times T2 is equal to minus Vbt, and this is the same as relation number 2 which we have obtained earlier. So, when we observe things in a relative frame, we can also solve the same problem with this method. So, we have seen this concept of relative motion, and with this we will end up our lectures on motion in one dimension. In the next class we will talk of motion in a plane, where we will look at position, displacement, velocity when a body is travelling in a plane, but to understand that we will also need a crash course on vectors. So, we will start with vectors and then we will talk of motion in a plane.